time travel is possible. It's a concept that has fascinated humanity for centuries, capturing the imagination of scientists, writers, and dreamers alike. The idea that we could move through time, just as we move through space, opens up a realm of endless possibilities and profound questions. It's a statement that sends shivers down your spine, a whisper of the impossible suddenly within reach. Imagine being able to witness the birth of the universe, to see the pyramids being built, or to meet your great-great-grandchildren. The very thought is exhilarating and terrifying in equal measure. But with great power comes great responsibility. The ability to alter the past or glimpse the future could have unimaginable consequences. The ripple effects of even the smallest change could alter the course of history in ways we can't predict. We haven't cracked the code, not officially. The scientific community remains divided on the feasibility of time travel. While some theories suggest it's possible, others argue it's nothing more than science fiction. Yet the quest continues, driven by our insatiable curiosity and desire to understand the universe. No time machines hum in hidden labs, no travelers from the future grace our streets. Or have they? The truth is, we don't know. The very nature of time travel means its secrets could be hidden in plain sight, woven into the fabric of our history. The truth is, we don't know. The concept of time travel is shrouded in mystery and paradox. If time travelers exist, they could be among us, their actions subtly influencing the course of events without our knowledge. The very nature of time travel means its secrets could be hidden in plain sight, woven into the fabric of our history. Ancient texts and artifacts may hold clues waiting to be deciphered by those with the knowledge and insight to see them. The allure of time travel is as old as time itself, from the myths of ancient civilizations to the cutting-edge theories of modern physics. The dream of moving through time has always been with us. It's a testament to our enduring quest for knowledge and our desire to transcend the limitations of our existence. Myths and legends teem with tales of bending time, of heroes and gods who could traverse the ages. These stories, passed down through generations, reflect our deepest hopes and fears about the nature of time and our place within it, of glimpses into the past and future. We yearn to witness history's grand events, to right past wrongs, to steal a peek at what tomorrow holds. The desire to control time, to shape our destiny, is a powerful force that drives much of human endeavor. We yearn to witness history's grand events, to right past wrongs, to steal a peek at what tomorrow holds, but the universe guards its secrets closely. The laws of physics, as we understand them, impose strict limits on what is possible, but the universe guards its secrets closely. Time, that relentless river, flows in one direction. Or does it? What if I told you the universe is not a rigid framework but a dynamic, ever-changing entity? Time, that relentless river, flows in one direction. Or does it? What if I told you the universe is not a rigid framework but a dynamic, ever-changing entity? What if the past, present and future are not separate chapters but threads woven together in the grand tapestry of the cosmos? What if I told you the universe is not a rigid framework but a dynamic, ever-changing entity? What if the past, present and future are not separate chapters but threads woven together in the grand tapestry of the cosmos? This is the promise and peril of time travel. What if the past, present and future are not separate chapters but threads woven together in the grand tapestry of the cosmos? This is the promise and peril of time travel. Our understanding of the cosmos, guided by the language of physics, suggests that the journey through time may not be a mere fantasy but a tantalizing possibility. This is the promise and peril of time travel. Our understanding of the cosmos, guided by the language of physics, suggests that the journey through time may not be a mere fantasy but a tantalizing possibility. To understand this, we must delve into the mind-bending world of Einstein, wormholes, and the enigmatic realm of quantum mechanics. Our understanding of the cosmos, guided by the language of physics, suggests that the journey through time may not be a mere fantasy but a tantalizing possibility. To understand this, we must delve into the mind-bending world of Einstein, wormholes, and the enigmatic realm of quantum mechanics. These concepts challenge our perceptions of reality and open up new avenues of exploration. To understand this, we must delve into the mind-bending world of Einstein, wormholes, and the enigmatic realm of quantum mechanics. These concepts challenge our perceptions of reality and open up new avenues of exploration. The journey through time is not just a flight of fancy, but a profound quest to understand the very nature of existence. Albert Einstein, a name synonymous with genius, gifted us with a revolutionary understanding of the universe. His contributions to science are immeasurable, but perhaps his most famous and transformative work is the theory of relativity. His theory of relativity, often whispered in hushed tones, holds the key to unlocking time's secrets. This theory isn't just a set of equations, it's a profound insight into the very fabric of reality. Einstein shattered the illusion of time as a constant, revealing it to be a dance, a graceful waltz with gravity. Time, as we perceive it, is not a rigid, unchanging entity, but a dynamic, flowing dimension intertwined with space. Imagine space-time as a vast, flexible sheet. This sheet can be stretched, bent, and twisted by the presence of mass and energy. The more massive an object, the more it distorts this cosmic fabric. Planets, stars, even you and I create warps in this fabric, like bowling balls on a trampoline. The heavier the object, the deeper the indentation it creates. This warping effect is what we perceive as gravity. This warping, my friends, is gravity. It's not just a force pulling objects together, it's the very shape of space-time itself, curving around massive objects. And what's even more profound is that gravity doesn't just distort space, it distorts time itself. The stronger the gravitational field, the slower time flows. Time flows slower near objects of immense gravity. This phenomenon, known as time dilation, means that a clock placed near a massive object will tick more slowly compared to one far away. Think of a clock placed near a black hole, that cosmic monster with gravity so strong that not even light can escape. Near such an object, time would slow down dramatically. Compared to a clock here on Earth, time for that brave little clock would slow to a crawl. This isn't just theoretical, it's a real phenomenon that has been observed and confirmed by scientists. It's a real phenomenon observed and confirmed by scientists. Experiments with atomic clocks on airplanes and satellites have shown that time, indeed, flows differently depending on the strength of the gravitational field. Now imagine harnessing this principle, warping space-time to such an extreme that it folds back on itself. This concept, though it sounds like science fiction, is grounded in the mathematics of Einstein's equations. This, my friends, is the theoretical foundation of a wormhole, a shortcut through the cosmos. If such structures exist, they could potentially connect distant parts of the universe, making interstellar travel a reality. Wormholes, those tantalizing wrinkles in the fabric of space-time, are theoretical tunnels connecting distant points in the cosmos. Imagine stepping into one end and emerging light years away in another galaxy, or perhaps another time. While still firmly in the realm of speculation, wormholes offer a tantalizing glimpse into the potential for time travel. Imagine the universe as a loaf of bread dotted with raisins. Each raisin represents a point in space-time. Now, a wormhole is like a tunnel bored through the bread, connecting two distant raisins. Instead of traveling the long way around the loaf, you could zip through the tunnel, taking a shortcut through space-time. The mathematics of Einstein's equations allows for the existence of wormholes, but mathematics and reality are two different beasts. We've never observed a wormhole directly, and their existence hinges on exotic forms of matter with bizarre properties like negative energy density, yet the possibility remains. Perhaps, lurking in the depths of space, these cosmic shortcuts await discovery, ready to unlock the mysteries of time travel. The universe, my friends, is full of surprises and wonders. If general relativity provides the framework for time travel on a cosmic scale, quantum mechanics, the physics of the very small, offers a different perspective, one where possibilities reign supreme. While general relativity deals with the grand tapestry of the universe, weaving together the fabric of space and time, quantum mechanics delves into the minuscule, the realm of particles and waves, where the rules of the game are entirely different. In the quantum realm, particles don't obey the same rules as everyday objects. They dance to a different tune, one dictated by probabilities and uncertainties. Here, the classical notions of definite positions and velocities break down, giving way to a world where particles can be in multiple places at once and where their properties are not fixed until they are observed. They exist in a haze of probability, capable of being in multiple states at once. This phenomenon is known as superposition, a fundamental principle of quantum mechanics. It suggests that particles can exist in a combination of all their possible states simultaneously, only collapsing into a single state when measured. Imagine a single particle, a tiny speck of existence. In the classical world, we would expect this particle to have a definite position and momentum, but in the quantum world, this particle is a wave of possibilities, a cloud of potential states. Now imagine this particle not as a solid point, but as a wave of possibilities spread out across time and space. This wave-like nature of particles is a cornerstone of quantum mechanics, and it challenges our classical intuitions about the nature of reality. This is the essence of quantum superposition. It means that until we observe the particle, it exists in all its possible states simultaneously. This idea is not just a theoretical construct. It has been confirmed by countless experiments, such as the famous double-slit experiment, which shows that particles can behave like waves, creating interference patterns that can only be explained by superposition. Until we observe it, the particle exists in all its possible states simultaneously. This observation collapses the wave function, forcing the particle to choose a single state. This act of measurement is a fundamental aspect of quantum mechanics, highlighting the strange and counterintuitive nature of the quantum world. This concept, as mind-bending as it is, has profound implications for time travel. If particles can exist in multiple states across time, it opens up the possibility of manipulating these states to influence events in the past or future. This idea is not just science fiction, it is a topic of serious scientific inquiry, with researchers exploring the potential of quantum entanglement and superposition to achieve time travel. If particles can exist in multiple states across time, could we harness this quantum weirdness to send information or even ourselves through time? Quantum entanglement, where particles become linked and instantaneously affect each other regardless of distance, could be the key to unlocking this potential. By entangling particles across time, we might be able to send messages to the past or future, creating a form of quantum communication that transcends the limitations of classical physics. Some theories suggest that by manipulating the quantum states of particles, we could potentially influence events in the past or future. This manipulation could involve using quantum computers, which leverage the principles of superposition and entanglement to perform calculations that are impossible for classical computers. These quantum machines could one day allow us to simulate and control quantum systems, opening up new possibilities for time travel and other advanced technologies. It's a concept fraught with paradoxes and uncertainties, yet it underscores the fact that our understanding of time is far from complete. The idea of time travel, whether through the lens of general relativity or quantum mechanics, challenges our deepest assumptions about the nature of reality. As we continue to explore these frontiers, we may discover that the true nature of time is even stranger and more wondrous than we can currently imagine.